Enough? What do you think?
Yes, I think we can start, Antonio.
Okay, well, thank you very much. Let me close the door. Thank you very much for this opportunity. I have an impossible mission this afternoon. I have to explain everything about climate in about 4 hours. I think that's the time they gave it to me. I'm not sure. That's probably impossible. So what I think I would like to do is that I would like to put some ideas so that you can go away with a few food for thought on your radar screens when you go away. And the title of this talk was Avoiding to be Ambushed by the Future. And, there are ambushes in the future for all of us. And of course, that has been a major, people knew that. And of course, natural phenomena were a major source of ambushes. And so people have been worrying about the weather for a long time. Well, what you see here is a painting by Raphael. It is, obviously, there are a lot of people laying around with no particular purpose, and there are very few books. So it's clearly university. This is actually the School of Athens by Raphael. And it is relevant to our story because the two old guys in the center of the painting are, one is Plato, the other one is Aristotle. And Aristotle is part of our story because he wrote the first book of meteorology ever written, the Meteorologica, in which he starts from the natural phenomena and the two create a theory of the natural world and we would say of the physical world. So that in some sense it was the first, the only time that physics was a part of meteorology and not the other way around. So in this book called De Meteorologica, and of course in the typical representation, Raphael is painting it with the book in his hand so everybody can recognize that's Aristotle, that's the ethics. He wrote this book, De Meteorologica, and those of you that have made classic studies can now help me to translate this small piece. Of course, in remote, cannot really be done. So maybe I should do it myself. So if I do the translation, the interesting thing is that it's talking about climate change. It's saying that the climate of Greece has not always been the same, and that can be proved by what? By taking measurements? No, by reading Homer, that basically show that in the Iliad, the climate as it was described in the Homer's poem was different from today. And therefore, this shows that climate has changed. Now, that's interesting. That's not what we would do today, right? If you have a question about the natural world, you would not go and read the literature or romance. You actually try to make a measurement and see if that statement can be supported by observation. But that was not Aristotle's point of view. And this is giving you the measure of what we have achieved, what we say when we say that we use science to actually investigate the natural world. So that's the main difference. And natural phenomena continue to fascinate the old natural philosopher. This is Seneca that is discussing about the question that lightning is caused by clouds colliding. But he realized that there was a difference between that vision of the Romans and the vision of the Etruscans. And the difference is that both of them are really expert in the interpretation of lightning. And the reason was lightning was supposed to be a message from the gods. But he says the Etruscan thinks that the Romans thinks that when clouds collide, provide lightning. The Etruscans think that the cloud collide for the purpose of making a lightning, and that's the whole difference. So it's the difference between an objective world that obeys laws that are independent from us or from our world, and a world in which the laws are not really objective. So this is another example in which we start having a consideration that the nature can have laws that are in some sense apart from what are our intellectual construct. So people slowly start to construct a scientific vision of the natural phenomena. And in the meantime, the climate was really changing. In the Middle Ages, we had what we call the Middle Ages Optimum. That was a situation in which, especially in the North Atlantic, temperatures were relatively mild. And so the Vikings were able to colonize Iceland and even Greenland. And Eric the Red, this is a photograph of Eric the Red, traveled even to probably North America and Newfoundland. And the settlements in Greenland are very well documented. At some point, there was a bishop there. But when this warm period ended, somewhere later in the about the end, in the 15th century, then the whole thing went the other way and things got colder. That was known now as the Little Ice Age. The Little Ice Age is basically colder temperature all over Europe, and the freezing was common in Central Europe. Actually, even in Venice, the lagoon was freezing in winter. So this was another change that can be documented somewhat. So the climate was changing, but people's perception were, continuing to, in a way, to have a very particular view of this. Or let's put it this way: people have difficulty in understanding the changes in climate. You must have an aunt that says that there are no more mid-seasons. Well, she's in good company. This is Leopardi, an Italian poet in the beginning of the 19th century, where he's writing in one of his diaries that the order of seasons is being perturbed. And in Italy, everybody knows that mid-seasons are not there anymore, and things are getting colder with respect to my youth. And that's interesting. So, oh, by the way, if you really want to look at it carefully, you'll find out that mid-season in the Mediterranean region do not exist, but this is another story. But let's see, can we check if it was right? Well, we can check because we can reconstruct temperature way back. And so if we look roughly around the 1800 period where Leopardi was writing, we don't see any particular strong change. So people have ideas that don't always collimate what the weather and the climate is doing. And we will continue, for some reasons, weather having bad press. This is Lorenzo Stecchetti, also known as Olindo Guerrini, and also known as Argias Bolenfi. He was an active protagonist of the capigliatura at the end of 19th century in Bologna. He was actually a librarian of the University of Bologna. He was a poet and a socialist and a radical, and he wrote a number of interesting things. And he's upset with spring. So here is a small sonnet where he's really damning the spring, because when there is spring, there are leaves on a tree. I cannot see his bow on the other side of the tree. So again, it's the fault of spring, and it's not clear why. But of course, this obsession with spring reaches the real maximum when Eliot wrote The West Land, and in the first place, he started by saying April is the cruelest month. So bad press is continuing with weather. And to tell you the truth, if you look at the variation of temperature in over a typical year, April is not particularly cruel. So, basically innocent. So I don't understand the reason for this real bad mouthing of spring month that is pretty decent. But weather really can continue to stay into the literature. This is the start. One of the most exceptional book ever written is The Man Without Quality. And okay, this is in Italian, but the original was in German. So, I mean, there's not a big difference. But the interesting thing is that this is a rather detailed technical description of a meteorological situation over Europe that basically ends by saying, well, basically it was a great day of August of year 1913. And so this is nice because that sort of give you how you can watch at the same thing in a number of different ways. So the question is that people have been looking at the natural system in many ways, many different ways. And because these, the climate, or if you want, the atmosphere and the ocean are something that can be experienced in a direct way, this variety of point of view was generated. So we have a literature on the weather. We have an operational view of people that work with weather. So we have a vision of the weather and the atmosphere and the ocean by mariners. So sea captain will have a different view of what's important for them and so on. So this is peculiar because usually science require a certain level of training and sophistication to just arrive at the point of defining the object of their study. In this case, the object is there. So what is happening is that people construct, or let's put it this way, it's difficult to arrive or overcome the personal preconception that everybody has when you talk about this, because everybody thinks they have a direct experience of what the climate system is. So a proper scientific approach is sometimes, this way, requires this extra effort. So let's present the climate system. Let's try now to give you the elements of what is a rigorous discussion of the climate. So what is the climate system? Well, the climate system is made of the atmosphere, the ocean, the land, biosphere, the ice, the sun, and everything is sort of kept together by water. Water has this awful property that changes phase. So you can find liquid water, you can find solid water, it's called ice, or in gas form, that's water vapor. And every time it changes phases, is actually exchanging energy with the environment. So every time a droplet of water evaporates or condenses or melts from ice, energy is exchanged. And this energy is released into the environment and comes into play for the regulation of, we will see, of the motion of the atmosphere and the ocean. So the climate, what is climate? Well, climate is the results of all these trillions of interactions. But as I said, water vapor crystallizes energy in its state, but of course it doesn't create energy. It's what we call it is a vector, is an energy vector, transport energy very efficiently. But the source, the only source of energy is actually the sun. So what's happening is that the sun, it's radiating energy over the earth, and this energy is entering the climate system in various ways. A lot of it goes in the form of water vapor, and then it gets into, affects the circulation in various ways. So the climate is the state of equilibrium that the atmosphere, ocean, ice, biosphere, our planet reach, that is in equilibrium with a given solar radiation. Well, if you look at this, you say, well, okay, this is complicated. It's very complicated. And at some point, the word just stopped being meaningful. But one might say, well, okay, you know, science operates through simplification. Usually you take a very, messy problem, and then you decide that we're going to throw away this, we're going to throw away that. And then you arrive at some sort of simple problem you can treat. So we can do that here. We could, say, okay, forget the water. Let's study the climate without the water. And you can do that. It's marginally simpler, but it's not our planet. So the problem we have here is that we have an irreducible problem, from the system point of view. We can change it, but if we change it, we change the problem, so we get a solution that does not apply to what we wanted to study. So that is a little bit of a problem. Then if you look at the issue from another point of view, you might say, well, the Earth is a very big place. I'm not really interested in what's happening on the other side of the globe. I'm living in Italy, so I'm interested in the climate of Italy, so I will instrument to death Italy, and then I'll break the back of the climate problem in Italy and forget the rest. Well, it's not really a very wise choice. It was recognized rather early, and it was interesting that this was done by a guy that was not a meteorologist. It was actually an economist whose name was Gibbons. Gibbons was mystified by the fact that India was hit by a number of almost regular drought episodes. So the agriculture was collapsing almost in the regular cycle in 61, 66, and so on. And he also found out that when that was happening, it was not only India that was going in trouble, but also other places on the world, especially China and Brazil. So he developed a theory by which these agricultural collapse were caused by the sunspot cycles. And then he proceeded to come up with a predictive theory that would predict the next crisis. And unfortunately, that didn't work very well. And, it was sort of discredit. And so that was the end of the story. But of course, he was in a way a victim of sunspot cycles. He has not been, probably was the first, but not the last. Other people have been victim of sunspot cycles. But he, however, was actually, he put his fingers on something that was there, but he didn't really have all the instruments to really discover it. That task fell on Sir Gilbert Walker, that was the director of the India Meteorological Service. And he basically did a major study of try to correlate everything with everything else. He tried to correlate weather variation in one place of the British Empire with other places. And in so doing, he found out that what Jevons has in sort of intuition was basically right. There were places that were connected. And now that idea that the climate variation on one side of the Earth are connected with the other side are very well formalized, and we call them teleconnections. And what's happening is that when the sea surface temperature in the equatorial Pacific are changing, they're affecting the sea surface temperature in the Indian Ocean. And because by so doing, they're shifting the prevalent precipitation pattern, then when these temperatures are changing, also precipitation in Brazil is affected, and the Indian monsoon is affected, and the precipitation in equatorial Africa. And because this precipitation release enormous amount of energy in the atmosphere, also the major circulation patterns in the mid-latitudes are affected. And so when the tropical Pacific is one of these states, basically the whole northern hemisphere goes into a state of excitement. And then there are impacts that reverberates all over the globe. These teleconnections then are a sort of a dead knell, in the sense that basically they kill the other simplification opportunity that we might have. We might say, oh, okay, so we'll look for a geographical simplification. It turns out that cannot be. So what shall we do? Now we're really stuck. Now we cannot simplify the problem from the systematic point of view. We cannot simplify the problem geographically. What shall we do? It seems that the scientific program is failed. The scientific program of reduction and simplification, by which we take a complex problem and we reduce it to something that can be understood and ultimately can be put to an experimental test, has failed. But this is how science proceeds. This photograph is a famous experiment, such experiments that brings you to the cusp of the development, in which you're really able to decide if you need to go one way or the other, are called crucial experiments. And that photograph is the experiment by Murchison and Morley. There was the experiment that basically demonstrated that there is no ether. But if you don't know the detail, it doesn't matter. What matters here is that this experiment changed our vision of the world and also opened up to an incredible series of discoveries and changes that have shaped the modern world. So the history of the world has been changed by two guys working in what looks like a basement on a table. That's a crucial experiment. Now, I would like to make a crucial experiment with climate very much. I would like to close Gibraltar and see if the Mediterranean really dries up 2 meters per year, as our calculations are telling us, or not. Or I would like to remove all the Alps and see if the climate of the Po Valley is really depending on the presence of the Alps. But they don't make me make those experiments. They don't give me the money. They don't give me the permissions. So the question is, how is possible a scientific investigation of climate if we cannot apply the scientific method program to it. So this is a big dilemma, and of course that crippled the development of climate as a science, as a quantitative science. If you read the climatology books of the 19th century, they look like a travel book. They look like I was in Sumatra, and in the morning was cold, and then it got warm. I mean, they look like a travelogue, okay? I think, so the fact that you cannot make experiment was really a problem. So the transformation of climatology into a quantitative science was possible when we had the possibility of making experiments. And how to make experiment? Well, in order to make experiments, you need to have, a set of control situations. So we need a set of control Earth planet on which you could make experiments, and we cannot do that in analog mode. But we had a real a piece of luck in this story, and the question was that we already knew the equation of climate. We already knew the equation that regulates the motion of the atmosphere and the ocean, their energetic relation and their thermodynamical properties. We were able to write them down. But there were complex equations. Actually, they're the results of 19th century science. So, if you're thinking about fancy, in a way, they're not fancy looking, but I can tell you they're pretty tough equations. They're so tough that we don't know how to solve them. So we don't know how to solve them using, what people say in closed form, by using just pencil and paper. So we had the equation, but we didn't know how to solve them. So that was sort of useless until people realized that we can make a trade-off. We can exchange the mathematical complexity of those equations with an enormous number of simple calculations. And we were exploiting the fact that we could do that in a systematic way. Once you've done that, if you accept that, then you can construct elaborate mathematical systems that will mimic the behavior of the Earth climate system. And then in those virtual representation of our planet, then you can make the experiments that we were discussing before. You can close Gibraltar and see what happens. You can actually eliminate the Alps. Oh, by the way, without being too stingy, you can eliminate all the mountains of the Earth and see what happens. And so you can make hypotheses, you can test hypotheses, and you can actually try to make a quantitative approach and apply the whole method that we have perfected over the last 200 years. By the way, not a lot. Aristotle was around for more time than our scientific methods has been around. So try to stick to it. As I said, these are the equations. I always show them. In case some of you found the solution, please contact me immediately. You never know. But, they're complicated, but that's not the point. The point that is really important are the symbols on the left. Those symbols on the left, the sort of squishy delta, and then we call it DDT. But what really is an indication of the time of change of that quantity. Basically, these equations are saying, look, the time of change of the wind, the first equation, is equivalent to a bunch of stuff that depends on a lot of other things, okay? But the problem is, because that is a rate of change, is basically connecting two different instants in time. It's basically telling me what is the increment between one instant to the next. And if that's the case, then I can use this expression to actually compute the wind a little bit farther in the future. If I know everything there's on the right, this equation, I can actually compute a little bit in the future. That's the key point. because by repeating that process, then I can march through time, and calculation after calculation, time step by time step, I can actually go into the future. It is absolutely amazing that I can do that with the people that we have been able to find out methods that allow us to do that, actually maintain the basic properties of the equation through a very long time. Modern models will have what we call a time step. This means the amount of time that every single calculation can bring you into the future of a few minutes. Nevertheless, we can march through time for thousands of years. And the basic property of the models would be preserved. For instance, mass. You don't want to lose your atmosphere or your ocean while you're doing this, right? That would be a disaster. So the calculation must be done in such a way that the total mass of the fluids that you are considering are conserved. We're capable to conserve mass to an amazing degree for thousands of years. And that, I would say, is an amazing accomplishment. So the take-home point here are, because we have this equation, they're amazingly complicated, but that's not the point. But what we can do is that we can compute all the climate fields. You see wind, temperature, water vapor content, and so on, as long as we can represent all the processes that interconnects these quantities a little bit in the future, and then we can actually do the experiments that we are designing. And this idea was due to an English mathematician, Lewis Fry Richardson. He wrote a book in 1922 called Numerical Weather Forecast. Actually, it was weather forecast with the numerical methods. That's wrong. And he was the first one to have this idea that you can actually substitute all those equations with the simple algebraic operation, basically sum and differences, as long as you pay the price of paying an approximation. And he used that grid that you see there. That's from his book. And basically, you take the calculation in each one of those points that is representing the entire area that is around it. And he tried to do what we would call these days a 24-hour forecast. So he tried to predict all the atmospheric variables 24 hours in the future. And of course, he did all the calculation by hand. And so it took 24 hours. That sort of defeat the scope, because if you want to do a 24-hour forecast and then it takes 24 hours to do the forecast, it's not particularly useful. But more dramatically, it was completely wrong. And so he was so depressed that he completely abandoned the idea, and he never dealt with the weather in his life as a mathematician, ever. And of course, there were very good reasons why he failed. He failed because he didn't know the property, both physical and mathematical, of those systems very well. We had to wait another 25 years for basically increasing our understanding. What you see here are the people involved in a project in Princeton. In Princeton at that time, John von Neumann was there, and they were building a new kind of computer. It was an electronic computer. You see, computer existed. There were huge mechanical machines, and which wheels were turning and rods, and so a multiplication would be made in, say, 4 seconds. But using the new vacuum tubes, John von Neumann and his team thought he could build a machine that would be able to make calculation without moving parts, so to speak. And so he would be able to do a multiplication in 3 or 4 milliseconds. And that was the idea. But John von Neumann needed a really tough problem to show the capability of the new computing system. And so he assembled this group that was tasked with the task of producing the first numerical forecast of the atmosphere. And these are people that played a lot of important roles afterwards. At the center, Jude Charney, that did enormous work. Jos Magorinsky on the right, that went on to found the Geophysical Fluid Dynamics Laboratory in Princeton, and other people. So that was one thing, was absolutely necessary. The other thing was that a refinement of the equation was needed, because what Richardson did not know was that those equations contains all sorts of motion. They contains actually the sound waves that I'm using right now to speak. From the sound waves to the large planetary motion that creates the teleconnection that I discussed before, all of these are dumped into those equations. And the price, let's put it this way, that if you don't treat carefully the really fast waves, like the sound waves, they will cripple your approximation and you will not be able to actually perform the numerical simulation. That's why the original effort by Richardson failed. So this kind of knowledge was not available. That was developed by Rosby there and by Charney through a series of theoretical work in the 40s. But all this knowledge was then put to work in the creation of the first numerical model and the first numerical integration that was performed in Princeton around the late 40s. So the numerical models for us are like the telescope for astronomers, or particle accelerator for the physicists. So they basically are major instruments that every new generation will allow you to look a little bit more accurately, extensively, and reliably into the working of the Earth climate. So it is like a major infrastructure that allows you to do science in new and original ways. And they are really infrastructure but they're basically software codes, but now they run easily into the millions of lines of code. So they're being built by many people, and they are now very detailed representation. As our knowledge of the processes and what's in there, it gets more and more extensive, then this description that is put into the models becomes more and more detailed and complete. And while all this was happening, we are, we're now at the early 50s, then the question arrived of how much we can predict, how far in the future we can predict. And it was unclear at the time. The original forecast was 24 hours for the entire Northern Hemisphere. But there was in the 50s and the early 60s, a continuous development of this model continued. And the question is how far we can predict was a major issue. And at that time, Edward Lorenz was a meteorologist working at MIT. And he was working with a simplified system, a highly simplified system. It was so simplified that only had 3 equations, actually. That was the sort of prototype of what everybody now knows as the Lorentz system. It actually those equations come straight from a very radical approximation of the atmospheric equation. What he found that these equations have very strange properties. They would be very sensitive to small changes. And he realized that if you change the starting point of one of these forecasts a little bit, then very soon the difference in the perturbation will grow in a way that very soon the two different the separation will be such that if you consider 2 different forecasts starting really close, then after a short time you will not be able to tell them, you will not be able to say that they were close at the initial time. So he was mesmerized by this, and he presented his work at a meeting of the American Association for Advancement of Science in 1969. Sorry, 1972. And that was the first time that he talked about the butterfly effect. The idea being that a small perturbation somewhere in the atmosphere may actually grow and cause very large deviation somewhere else. It was funny, it is funny that the idea that the weather can be really sensitive to small details actually have been around for a long time. A physics professor in Pennsylvania called Franklin wrote in a review of the physics books that had nothing to do with this, that he called it the grasshopper principle, that a grasshopper could cause a storm in Philadelphia if the grasshopper in Montana may actually perturb the atmosphere enough that there is a full storm on the East Coast. So the idea that the weather and the atmosphere is sensitive was around, but Ed Lorenz was the first one to really putting down in a rigorous term. But Ed was doing much more than simply stating that the atmosphere was sensitive to initial condition. He started the whole branch of mathematics, the one that we called initially was called chaos, and now is developed in the way a very wide area of research of non-deterministic systems. Strictly speaking, these are all differential equations, so they're all deterministic. But the point is, they're so sensitive to small changes. If you change the last significant bit in a weather forecast today, after 20 days, you will not be able to tell the fact that they were closer than one bit. So it's very strong, this sensitivity. But it started a completely new area of science, because basically it's telling us that the sort of nice, close, clean problem that we have learned to solve and love, all the little exercises that those of you that are in the sciences have done in school, those are a minuscule fraction of all the problems. They're not the rule, they're the exception. A typical system would be like Ed Lorenz butterfly system. It would be chaotic. It will be very sensitive to initial condition. And so our vision of the world is changing, is moving away from the 19th century sort of mechanistic, deterministic idea that the development of mechanics in 19th century gave us, and is moving towards a more probabilistic and statistic, guided approach. In some sense, is the classical mechanics equivalent of the triumph of quantum mechanics in the microscopic world. So it's interesting. This is started from meteorology. And again, this was a contribution to all our vision of the world. So the world changed again. Oops. And so this was when meteorologists were happy. This was when meteorologists were just dealing with the atmosphere. Maybe some oceanographers were looking at the ocean. And the worst problem we had was doing weather forecast. And then suddenly people realized that we are actually doing something to the planet. We're actually changing the way the planet is composed. And so we're sort of doing a gigantic experiment in which we're changing some of the fundamental properties of the planet by changing the atmospheric composition. And because of the extreme sensitivity to perturbation of the system, these changes that we are doing will be amplified. And so they will provoke large changes And one thing that we realized in the process was that most people take climate for granted. They assume that season will run one after the other, assume that you will get a certain amount of rain in the winter. Okay, maybe some winter will be a little bit worse, but then we recover, and then things will more or less continue in indefinite sequence. And so nobody was paying much attention to climate because it was a given, it was a feature, it was like a geographical feature. It's like a mountain. A mountain is there and it will be there. So when meteorologists start to realize that instead things are changing because we are changing a fundamental structure of the planet, it was a shock. And there was also a moment where people also realized that if you start thinking about a changing climate, well, this has an impact on a lot of human activities. And you can't really separate very well the human systems from the natural systems because of the series of feedbacks and impacts that are linking these two systems, the natural world and the social and human and the human world. Okay, that means both the social part, the economic part, but the economic and the social development are actually guiding the changes that we're doing to the system because they're guiding the amount of gases that we're putting in the system. And the major symbol of this change is the increasing amount of carbon dioxide in the atmosphere. This is the most famous measurement. This is a Mauna Loa observatory in Hawaii. Now there is a network of this observatory all over the place. There is one in Italy, nearby Bologna, Montecimone here. But carbon dioxide is so well mixed in the atmosphere that basically any of these measurements will represent the typical concentration of carbon dioxide in the atmosphere. Now, this is a very interesting curve. Well, first of all, it's growing, meaning that we are putting more and more carbon dioxide in the atmosphere. Carbon dioxide comes from burning fossil fuels, also by other human activities like deforestation, cement production, but basically it's fossil fuel. And there is a very visible seasonal cycle on it that is due to the biosphere activity. Basically in the spring, the plants absorb a lot more carbon dioxide when they're putting out leaves, and then they're losing the leaves in the fall, and then carbon dioxide goes up. But except this seasonal cycle, you can see that the curve is going up. And now the problem is that the carbon dioxide is not a neutral component of the system. The carbon dioxide is actually a very active element, because what it's doing is actually absorbing part of the radiation emitted by the surface. And so you can think of it as a regulator of the surface temperature. Increasing the amount of carbon dioxide will make tougher for the surface to get rid of the energy that's coming from the sun. And so you need to, let's see, yeah, okay. You need to increase the temperature at the ground in order to reach a new balance, because the Earth cannot really, store the radiative energy coming from the sun. It must be radiated away, and the balance must be reached. So if you increase, in some sense, the planetary resistance to get rid of extra energy by increasing carbon dioxide, the net result is that you increase temperature at the ground. And this is another famous symbol. This is the global surface temperature from average over land and ocean for the entire planet. And this goes down to last January 2021. So you can see that starting from last century, temperature is going up quite steadily. In the last 20 years is very, very noticeable. And this is, of course, this is an interesting fact because, you know, this index here, it's very nice, but it's a symbol. I mean, this is the average temperature. I mean, the Earth does not know anything about the average temperature. And in some sense, you can think of this like the Wall Street market index, okay? So it's an indicator. When the Wall Street market index is going up, some people may be losing a lot of money. And if that index is going down, some people can be making a lot of money. So the fact that we have this behavior globally for the planet is important, but it doesn't really tell us what is going to happen in every place on the globe. But the reason is the extreme variability that the atmosphere has and the climate. Just to give you a feeling, this is what happened in climate, let's say climate events in the 2020. Just to give you an overview. So for instance, in the tropics, we had a very active hurricane season, both in the Atlantic and in the Pacific. We had many storms way above average. And we also had a very rare tropical hurricane in the Arabian Sea. That's very rare. And we have been hitting warm records all over in many regions from Africa to Europe. We also had a very low sea ice extent in the Arctic. And we have extra rainfall over US. So you see, at the same time, some place of the world was experiencing drought, and some other place of the world was actually experiencing extra rain. So that's a typical issue that we'll encounter when we try to understand what climate does, especially if you pose the problem of try to quantify what are the possible changes that climate will produce. And just to give you a feeling, these are the average temperature in January 2021, so last January, with respect to a 30-year base. So you can see there are large warm anomalies over North America, over Africa, but there are very cold anomalies over Siberia. So that's how climate will express itself. It won't be, if you look at that increase in temperature, it won't be a very nice, steadily increase in temperature all over the place, you know, sort of nice and clean. But what will happen is that will be variation all over, and different areas will get different impacts. And now we are in the position to really look at a lot of various parameters. Why we need to do this? Because the multiple parameter view of the climate is such that you need to look at many different parameters. Some of them are not strictly linked to the sort of physical variables that we've seen before. For instance, upper left, there is a surface temperature, we've already seen that. But the two panels below are two derived quantities. That's the warm days and the cool nights. So that is the number of warm days, defined as days below a certain, above a certain local threshold. And this is now for the entire 2019 year. And so what you see is that Europe, for instance, exhibited an anomalous number of warm days. So we had 40 days more than usual. On the other hand, if you look at cool nights, then the cool nights were fewer. So Europe was experiencing fewer cool nights. So basically what was happening, we had more warm days and less cool nights. So temperature at nights were higher than normal. Temperature at nights are very important for a number of control of pests, for instance. We had a problem with the diffusion of invasive species that are really finding a comfortable environment because of this changing temperature. Usually they're controlled by cold winter nights. If you don't have the cold winter nights, then they survive the winter, and then they find a longer growing season with devastating effects. But this is to show you that once you have these mathematical models, you can actually use them to compute a number of different quantities. So you get a very sophisticated view of what the climate parameters are. You don't look simply at the temperature and winds and so on. We have, for instance, detailed information about water vapor, water. That's often is not as complete or nice as we would like. But if you start from precipitation, for instance, that's the bottom right. These are the anomalies in 2019 from the long-term mean. And you can see extensive drought over the maritime continent, over Borneo and in Indonesia, that is connected with a drought over Australia. Actually, if you look carefully, you see that in the Pacific, there is a pattern. If you look on the other side of the globe, so in the East Pacific, you see there is a dry zone that is surrounded by two extra rainy zones. So what, if you put it together, this is not a perfect projection. What you really see is a shift in the precipitation area. Basically, these anomalies means that the major precipitation zone have shifted. So they've moved from their usual position. So they've moved towards the east, over Australia and over west in the Indian Ocean. And this is typical. The climate changes that we see in precipitation especially are not so much changes in the total amount of precipitation over the globe, but there really are shifts in patterns that are more or less established. And this, of course, can have significant consequences. This is important, especially for the marginal places. One of the most marginal places is the Sahel. The Sahel is the region that is right south of the Sahara. Is a semi-arid zone, because what is happening is that during the seasonal cycle of in West Africa, the seasonal cycle of precipitation is such that there is a rain of precipitation that follows the sun. So it moves north in the summer and then goes south in the winter. It goes up and down. But there's lots of variability. So sometimes the rain reaches a little bit north than usual. And when that happens, that area gets a little bit of rain. So that happens, say, every 2 or 3 years. That's enough to maintain a semi-arid regime. That's a Sahel. Now, if for some reason the rain do not come for 10 years or 15 years, then that region transforms into a full-blown desert. So that's a problem in marginal zone. If you look at a phenomenon like this, it won't be a disaster on a global scale, but it will have a huge impact locally, because it will transform completely areas that are, in a way, already vulnerable to areas that are completely arid. So what can we do? Well, you see, once we have a machine that would represent climate, and once people realize that we are changing the composition of the atmosphere, it was obvious to ask yourself, oh, okay, but then I can sort of find out what kind of climate exists if I hypothesize a certain distribution of carbon dioxide. So this was how, in a way, the climate change experiments were born. That was in the early 80s. The data amount of law have been collected since the 50s, but the instruments to actually be able to really evaluate the impact of those growing carbon dioxide concentration on the climate were not really fully developed until the late, maybe early 70s, so to speak. So at that time, there were, in a way, still rudimentary tools, but people tried to use them. But the concept is very simply said. Somebody has to make an hypothesis of how much carbon dioxide will be in the atmosphere. And then I can compute by using one of these models, the climate that is in equilibrium with this carbon dioxide. And the first experiments were very drastic. People doubled the amount of carbon dioxide, or even quadrupled the amount of carbon dioxide. And then we see what the surprise was that if I go back to that picture, to this picture, what you see here that we haven't really discussed is the scale on the y-axis. The scale on the y-axis is in part per million. Okay, now part per million is a small number. You would agree with me. The percentage increase is enormous because we've gone from basically 280 to 420. So we have added 140 units, basically is an increase by 50% over the pre-industrial times, as we say. So 280 was the concentration before the Industrial Revolution, say in the 18th century. We have now reached 420, okay? But still, 50% of a small number is still a very small number. I mean, if you have to buy a house that costs €1 million and you have 280 euros, you're probably a little desperate. But then a friend of yours comes and says, oh no, don't worry. You know, I will increase what you have by 50%, and it gives you 140 euros. Now that's a big effort, but you know, you're not very close to your target. So the first reaction to watching something like this would be, all right, so what, okay? That's a small number, it's growing, but still a very small number. So why should I worry? Well, you should worry because we have found out that the atmosphere is very sensitive to small changes. And there is a chance that this particular small change will not do anything. But there is also another chance that this particular small change will actually do something. And that's what those early experiments in the late 70s and 80s showed that even this small change may actually have finite changes in the surface temperature. And that is, of course, an interesting point. So those experiments showed that we have a serious problem at hand, that the changes that we are doing to the atmosphere are significant. So from that moment on, developed a whole enterprise, I would say, trying to find out, well, first of all, remove all the lingering doubts of if this was real, if this was happening. Also removing some illusions that the Earth would magically have a mechanism to counteract the effect of increasing carbon dioxide. So all this has been vetted, and we have now come to this conclusion. And of course, the issue became of such social and geopolitical relevance that in a way it was necessary to set up a new organization. The point was that this was an example of a problem that has an enormous, it was generated by science, okay? All right, I admit it was our fault. We did the experiments, we started it, so it's our fault. So the whole mess started because scientists had an idea and they tried to find out what was happening. So there is an enormous scientific content, okay? A result of an experiment may actually change the terms of the geopolitical conversation about what to do, and also the direction of the decision-making process. So science was important, but science is a human activity, and scientists are just humans like everybody else. So they may bias, they may be influenced. So, they're just historical actors, as they say. So the idea was to try to create a process by which a source of authoritative information about the situation of climate was set up. And that was established by the UN under the sponsorship of the World Meteorological Organization and the United Nations Environmental Program, UNEP. They set up something that was called IPCC, International Panel, an Intergovernmental Panel on Climate Change. That is an international organization that has the task of producing assessments. What's an assessment? An assessment is an analysis of the state of knowledge. So they don't do any new science. They basically look at what the science results are, and then they come up with the report that basically say, well, that's the status of what we know. And this is the degree of reliability with which we know what we know. These are the things that we know we don't know. And these are the things that we don't know we know. No, I'm joking now. But that is more or less the logic, okay? So the logic is to try to set up a place, if you want, a safe space, where a science conversation can be held and the general consensus of the degree of knowledge is reached. Now, if you want to do that, however, you also want to be interested in what the climate will be if the present behavior continues. So what's the present behavior? Well, we're putting an enormous amount of carbon dioxide in the atmosphere. And what we see here, that's represented by the black line. The black line are actually the amount, the emission from land use and fossil fuel in gigaton of carbon dioxide per year that we put in the atmosphere. Now that stops today, okay? That stops at 2020 or about. Now, what about the rest? Well, the rest, we have to make hypotheses. And social scientists and economists were able to devise ways in which we can actually try to make stories about the future. Basically, if, I'm a climatologist, so I can compute the climate if somebody's telling me how much carbon dioxide, other gases will be in the atmosphere for a period. Nominally, these days we look at the period until the end of the century. So what you see, all those colored lines are different vision of the future. They're different storylines. They're basically visions in which the top line is a word in which we will not do anything, and demand for fossil fuel consumption will keep growing. And so injection of carbon dioxide and other gases will go unchecked. And therefore, we will get a pattern of emission that more or less resemble the gray curve. The other curves correspond to different choices that are to be made in the future. Of course, as you go down the colors, as you go down, more and more, the hypothesis is that more and more measures to contain the usage of fossil fuels will be used, and so the emission will be decreased. Now, in some sense, this is to be expected, right? So, if you're careful about putting carbon dioxide in the atmosphere, then the emission will go down. Then, for each one of these scenarios, one can compute what kind of climate I will get. Actually, I can get detailed description of the climate. I can actually produce all those maps that I showed you for each one of these lines. So I can tell you what will be the precipitation. Well, what will be? I have to qualify that statement. What kind of precipitation distribution is generated by the middle scenario or the other scenario, something like that. But we are indexing the overall size of the impact by the global warming at the surface. So when I say that the high-end scenarios will result in the warming between 5 and 6 degrees, I'm actually pointing to a situation where the changes induced by this emission in the climate variability will be very high. And as you go down with the emission, then the global impacts is getting smaller. But you can see that in order to get what people now have officially adopted as the target of the political action, this means keeping global surface warming below 2 degrees. Some of those lines will have to drop under the zero line. Now, if you drop under the zero line, your emissions are becoming negative. Negative means that you have to remove carbon dioxide from the atmosphere. Now, that's a big challenge. A lot of people are trying technological methods to remove carbon dioxide from the atmosphere. At the present time, I'm not aware of any real practical method. I think there are two obstacles. One is that, of course, you have to make sure that the method that does not create more greenhouse gases that carbon dioxide that removes from the atmosphere. And the second one is that they must scale, because don't forget that on the y-axis we are measuring this emission in gigaton. So you have to remove enormous amount of carbon from the atmosphere, and so your method to removing the greenhouse gases must scale to a very large amount. At the moment, the only effective method that we have to remove carbon dioxide from the atmosphere is planting trees. That works, but it's a sort of a short-term kind of measure. It also has a large requirement of space, so it's conflicting with agriculture, with food production. So it's messy.
Antonio,
yes.
I just wanted to alert you that there are two questions on the chat. And the second, usually we make a break.
Okay.
Yeah, I just tell you some information on the timing. You have 3 hours, which means a total amount of time of 45 minutes times 3, which is 2 hours and 15. And I think you have been teaching for 1 hour and a quarter. So I think that if the students agree, you may make a break now after maybe answering the questions, and then teach for 1 more hour. And the break now will be 15 minutes.
Yeah, that's fine. This is a good place to stop. So I think we can stop now. Okay.
And about the questions, if you want to take a look, you have to just...
Sure. Let's see, where are the chats? I have to look at the chats. Wait a minute. I've lost here. Okay, I'll stop sharing for a moment. Okay.
Yeah.
Okay. Okay. Okay, well, okay, regarding the first question, oh, you can read the question, so I don't need to reread the question. Yes, that's absolutely true. The same equation are used for short term and long term, but let's put it this way, there are a lot of details that need to be fixed in those models, because what I have not said is that the detailed representation of the processes that are involved in those equations is not univocal. So people may choose different ways of doing the same thing. For instance, rain can be generated using a different algorithm, different ways, okay? That corresponds to basically different level of accuracy and cost that you're willing to pay. So all these choices are slightly different in their results. And so people may choose a different set of choices if they're really targeting, say, 10-day forecast, or if they're instead targeting the Ice Age problem, or the next 100 years. These days, there is a strong movement towards unifying the formulation completely. That's what is named as a seamless prediction. For instance, we do that. At CMCC, we use exactly the same model with the same formulation, from the short-term forecast to the climate scenario that we do for IPCC. The idea is that if we stick to the proper representation of physical processes, we get a more a better physical treatment of the problem, and we don't put much empiricism into the system. Okay, so there is a strong movement to do exactly that. Regarding afforestation efforts, there are many. They're doing the same in China. They're trying to protect Beijing from the wind coming from the desert through a green wall. To tell you the truth, I'm not sure it's going to fix the Sahel problem. By the way, the Sahel went through a disastrous drought in the last 20 years, but now things are recovering. And so I'm not sure if that's going to fix the Sahel problem. Actually, I'm not sure it's going to fix the Beijing problem either. But people are, of course, making a lot of these afforestation efforts because they're part of the international negotiation on climate change. Maybe we'll say something later. So yeah, I'm not too sure, but the Sahel drought was very important because it started the attention of the international scientific community on the possibility of actually looking into decadal forecast. This means decadal. Now the range of forecasts has been basically pushed into the season, and there are very active investigations to see if it can be pushed into the multi-year time scale that, just to summarize, is called decadal forecast. And the Sahel variation of precipitation that happens over a multi-year scale were the one that triggered all this interest. Not that they've been solved, but there is a lot of investigation going on. Okay.
Okay, I think we can make a break.
So we make what, like a 15 minutes break, something like that?
Okay. Yeah, that's fine. Thank you, Antonio.
All right.
Oh, okay. No.
I think you can start whenever you want,
Okay.
Antonio.
Okay, great.
For 1 hour more, up to 6:15.
Okay, I'll try. Okay. So we were about here. So what I would like to do to show you is just an example of what happens in our region. The Mediterranean is a special place. You know, Mediterranean is a boundary area, is a boundary historically, geographically, socially, economically, and is also boundary meteorologically. Is actually separating the mid-latitude zone from the subtropical areas. And this is creating a peculiar situation because basically the seasonal cycle between winter and summer is essentially an oscillation of this boundary in the latitudinal direction. So you can think that in the summer, the Mediterranean is North Africa, and in the winter, the Mediterranean is in Central Europe. So basically, we have this dry and warm summer, but we get you know, abundant precipitation in the winter, and so we create the Mediterranean climate that we like so much. So so it's a bordered zone. As every bordered zone is in the little bit the same discussion that we said regarding the Sahel applies to the Mediterranean. The bordered zone are vulnerable. Because you can think what happens. What happens is that a small change in the location, the average location of that border, will have much larger consequences in terms of the dominant climate over the region. You can think that if the climate would shift permanently south, the Mediterranean will be a much wetter and cold place than it is now. Or if it does the opposite, then things will change in you know, the opposite direction. And actually, so the question is what the Mediterranean will do with the increase in greenhouse gases. That's a question that we can ask by using our models, and that's what I'm going to show you. These are results for some scenarios that we have done, and I'm just showing you the results that regards precipitation. The way these things are created is that, well, first of all, you need to have hypotheses about the amount of carbon dioxide in the atmosphere. These are known as the emission scenarios we discussed, and we're going to discuss it a bit more later. These are for two famous scenarios that are the previous generation, they're called RCPs. The details don't matter too much. Basically, you can think of it as the scenario on the left, there is, I'll leave it this way, the scenario on the right has a lot of carbon dioxide, the scenario on the left has somewhat less carbon dioxide. And what we see here are basically the difference between average condition towards the end of the century with respect to average condition in the past century. And what we're seeing here is the difference in terms of percentage of the present precipitation that corresponds to the later period of this century, so sometime towards 2100, okay? So this scenario are done with that's done by colleagues at CMCC and with using a very detailed model that is over the region you see. That it is expansive, so we cannot really use these models over the entire globe. So we use a special technique that's called downscaling. in which we use models that have coarser definition. So you have a smaller level of detail for the entire globe. And then we use models with a very high level of detail over limited regions that are driven by condition along the borders. So the condition on the borders are taken from the coarser model, and then they are imposed on the border of the high resolution model at basically very high frequency in time, maybe sometimes even every 3 hours. And in this way, the effect of the global climate is transferred into the local region, and the detailed model can actually develop the specific dynamics that correspond to the specific details of the ground, for instance, of the detailed orography, and so on. So what we learn from, or at least what we can discuss. Well, first of all, if we look at the annual mean on top, we see a general reduction in precipitation let's start from the really high concentration of carbon dioxide on the left, on the right, okay? So in the annual mean, you can see that there is a very, drop in precipitation, maybe, between 10 and 20%, 30% maybe. If we go in winter, what we notice is that actually precipitation tend to increase in northern Italy. Winter precipitation is lost in southern Italy and on the island. And in the summer, there is definitely a loss of precipitation. So the overall pattern that emerges is basically a reduction in the annual mean precipitation, and reduction especially pronounced in the summer, somewhat mixed feature in the winter, and something like that. If we put less carbon dioxide in the atmosphere, that's the left column, basically we see the same kind of behavior, but with smaller amplitudes. So reduction are reduced somewhat. You also notice a very high level of different behaviors. There are spots, even in Sicily, when in one of these runs, actually precipitation increases. Now, that's of course a real challenge that we face, right? The challenge that we face is that because the atmosphere and the climate is chaotic in the same that I described it before, does a single experiment it's enough? And what is the level of reliability with which we can use these results? Of course, we don't know. We don't know the answer. I cannot say, oh, you should use 5 experiments or something like that. We don't know, but what people are trying to do, they're trying to use multiple, they're trying to get a feeling of the range of results that, or let's put it this way, of the extent of the sensitivity of the climate to a certain carbon dioxide, testing different perturbation. So the idea is that because the concentration of the greenhouse gases is the same, then I have to evaluate what is the sensitivity of the climate with respect to this, in a way, fixed carbon distribution. That's, in a way, the internal variability of climate, the one that is intrinsic to the nature of the feedbacks and the processes. So we don't know. We don't have a theory. We don't know how to precisely say how many, how can we define this variability in a definite way. We are basically trying to get a hold of it by testing all sorts of different possibilities around the same amount of concentration, of greenhouse concentration. And we do that by perturbing the same model, the same representation of the climate system. But we also do that by using different models that have made different choices in the particular representation of the algorithm or the numerics, or even different computers. Because when we put them together, then basically we try to compensate for the errors that all these systems have done in different ways. And so if we put them together, we can hope to get an idea of what is the spread, what is the uncertainty of this scenario. So that's the whole enterprise. The whole enterprise is trying to understand what are the mechanisms, trying to evaluate uncertainty and spread. So what I'm showing you here is just an example, but it's pretty typical. So we cannot really, rely too much on the details of this picture in this particular form. But the fact there is, a large sort of feature, right? There is a very large thing. I mean, the precipitation is going to decrease more in the south of Italy and less in the north, in some cases actually increasing. So does that mean something? Well, it means something because if I now take a larger view, and this is actually done with a different model, this is the global model, and now I'm looking at the entire Mediterranean region, so I don't have limitation. Now, these are the results from an experiments made with the entire Earth. Well, what is happening is that I see a very similar general pattern, right? This is always precipitation. And you can see, especially if you look at the winter picture in the middle, you can see a clear signature of the decrease of temperature in the central South Mediterranean and the increase of precipitation in the Central Europe. So it looks like what we have seen in the high resolution downscale picture before is actually part of a larger pattern. Now that's in a way interesting, you see, because the global models are very good at capturing large patterns and they're usually very robust. The large patterns are robust with respect to the perturbation and the different formulation of models. So what we understand from here is that when we increase greenhouse gases in the atmosphere, we shift the prevalent areas of precipitation a little bit north. Technically, we say that what is happening is that we're shifting the storm tracks north. Now, what are the storm tracks? Well, we have seen all the storm tracks we have seen. Every time you look at one of those weather forecasts on television, they will be talking about perturbation and fronts coming from the Atlantic, and that's because the way the atmosphere works is that these large system will be generated over the Atlantic, and then they go through a specific life cycles of several days. So these storms intensify and have their own cycle. They usually arrive over Europe pretty mature, but they're essential in maintaining the energy balance of the atmosphere. They're essential in transporting water vapor from the tropics to the polar region. And they're, of course, carrying rain. So they're the reason why the mid-latitudes are basically a nice place to live. They're not too cold. There is lots of water. And so you can have abundant biological production. So there is a path of these storm tracks that goes over the Mediterranean. Oh, actually, over Europe, there are two of them. One goes straight over Central Europe, UK, Central and Northern Europe. And then there is another one, smaller, that goes over the Mediterranean. That's the one that takes the water to us. Now, what climate change does? Well, what increasing greenhouse gases concentration do is that they basically weaken very much the second storm tracks. and they intensify the first one. So basically they're shifting the storm tracks north. They're decreasing the number of storms that will reach into the Mediterranean. They will increase the number of storms that will go into Europe. And so the net result is that the Mediterranean will be with less water and the Central Europe will be with more water. And so climate change for us, the main expression will be a stress on the water resources. And above the Alps, then the problem will be flood and excess precipitation. So it's interesting because you have to realize that usually when we speak about climate change, people are always talking about drought. That's not the case. In some cases, climate change will express itself by actually increasing the number of storms, and so increasing the probability of flood. And guess what? These changes in precipitation and temperature, they're also bringing health impacts, because they are shifting the habitats of vectors like mosquitoes and ticks and other vector of disease. And so, for instance, this is creating a serious problem with Lyme disease in Central Europe, because wetter and milder conditions are making it more favorable for ticks to survive. And so and at the same time, the distribution of urbanization is getting more entangled with the natural environment. So people tend to mix with forested areas. So it's becoming a serious issue, just to give you a feeling. So these pictures show that the increase of greenhouse gases may actually be a serious problem that we have to consider in the Mediterranean. The uncertainty is still high, but these numbers are not insignificant. So these are all pointing to the fact that we have to consider this problem for the future, and we cannot simply ignore it. This is giving us a clear idea that we will have something that we have to consider very well. But you also see the beginning of the fact that the entire climate change problem has to be formulated as a risk evaluation problem. Given the uncertainty and given the variability of climate, what we can do, what we are able to do, is to try to evaluate the possibilities, and therefore trying then to evaluate the risk, and therefore taking measures that would alleviate the damage caused by climate change. So that's what IPCC, as I told you, was supposed to do. So IPCC was founded in 1988, and it is now, there are 195 governments that are now part of IPCC. And the task of IPCC, as I told you, is to assess on a comprehensive, objective, open, and transparent basis scientific, technical, and socioeconomic information relevant to understand the scientific basis of risk of human-induced climate change, its potential impacts, and options for adaptation and mitigation. And of course, the mission is that the IPCC is supposed to create these reports, and the reports should contain these assessments, and the reports should be neutral with respect to policy, in the sense that IPCC is not there's no advocacy institution. And so they have to report objectively scientific, technical, socioeconomic factors that are relevant for the application of particular policies. The hope here is that these reports may actually represent a set of options from which the decision maker can actually select whatever they want to do. That's the idea. But for the first time, or maybe the second time, we find this word, adaptation and mitigation. And I think it's important that we understand what they are. You see, there are two possible strategies. I mean, once you're convinced that we have a serious problem and that we have to do something, and so climate change cannot be ignored, we have basically two strategies. One strategy is that you say, well, this is really stupid, and we have to stop putting carbon dioxide and the other greenhouse gases into the atmosphere. Great. That's the main road, right? That's the ultimate solution. That's called mitigation. Now, the problem with mitigation is that because we're using the atmosphere as a global common, so everybody's dumping whatever they don't need anymore into the atmosphere, but the atmosphere is everybody's. So we are breathing air that probably went through Asia several times. So the air is everybody's, but we're using it like a common trash bin. So the problem is that if we don't find a coordinated action to stop that, the communities that are virtuous, so the community say that a part of the states will actually implement policy to reduce emission. If somebody else is not doing that, they will still have the damage of the emission of the other guy. So mitigation is an inherently cooperative problem, needs to be tackled at the same time all over the globe. That's why this is the task of the international negotiation, because we have to find an agreement among all the nations so that the same policy and the same attitude towards emission is reached all over. That's mitigation. On the other hand, you might say, well, I understand some climate change will arrive. Because some climate change will arrive, because I cannot mitigate in time, because other reasons I'll tell you in a moment. So what I have to be a pragmatist, and I have to say, okay, because some climate change will arrive, I'm making an all-out effort to understand what kind of detailed changes the increase in carbon dioxide will bring. Once I know these detailed changes, so at least I have a decent probability estimates of these events, I can actually put in place measures and policies that will alleviate the worst impact. For instance, if I find out that after extensive investigation, turns out that I cannot grow a certain crop anymore in a certain region, because I don't have enough water, or temperature is too warm or too cold. Then if I know it in advance, I can actually put up policies that will try to incentivize other crops so that I will maintain the social and economic texture and try to avoid the disruption of the social environment and of the communities that are living there. So that's called adaptation. Now, adaptation is very different from mitigation, because as much as mitigation was a global problem, or if you want, was a cooperative problem, adaptation is somewhat different. Adaptation put responsibility on the, in a way, social individual. Okay, so it's imagine two communities that they're growing the same crop, that is find out that you cannot grow it anymore, and then one community sort of activates and it prevents and you know, thinking in advance, start putting investments to grow new crops, and another one does not do anything. And then in 20, 30 years, then climate condition changes, and then the one community that has done all the investment in adaptation will prosper, and the other one will have all the problems linked to the decaying climate. So this means adaptation is a local problem, responsibility is local, and it is, in a way, you don't need elaborate international negotiation, because if you adapt, you will be better off. If you don't adapt, it will be on you, and your neighbor will not suffer because you have not adapted. So that is the difference between these two approaches. And now they're discussed in, as I said, in different ways. Just to give you some information on the cycle, this is the IPCC cycle. This is the 6th assessment cycle. And the main report is expected sometimes next year. This year, there will be presented the report of the 3 working group. Oh, by the way, IPCC is divided, is organized in 3 working groups plus a unit that is looking at the emission. The 3 working groups are basically looking at the first one at the natural aspects. So they're looking at, in a way, the more traditional meteorological and oceanographic and, physical part of the climate. So they will try to assess what we know of the present state of the climate and what we know when we use the scenario for the future. Working group 2 works with impacts. So these are the people that will look at the scenario results, the main climate drivers, so the changes in temperature, precipitation, and everything. And they will try to work out what it will mean for different areas, agriculture and ecosystem, and so on. The third group is the economic and socioeconomic aspects group. They will they work both in the definition of the emissions scenario. They also work on the evaluation of the aspects of climate change, what kind of impact there will be on economy and society in general. Each one of these working groups will produce a separate report that then will be put together into a synthesis report later. And also will be produced a even more synthetic report called SPM, Summary for Policymaker, that is usually the one that is most read by everybody. Unfortunately, because of the COVID situation, this time scale may be changed as some of the dates may slip, but we're almost there. The reports are almost done. Now, I've been talking about models of the atmosphere and the ocean, but once people realize that there are this close interconnection with the human system, then people start to put together numerical models that include the social and economic sectors. These models at the moment are using simplified version of the natural Earth systems model. They're known as integrated assessment model, and they would get as input the information from the drivers, the climate drivers from the natural Earth system, and then they will try to model the society into its aspects with the energy consumption and the food production, the overall economic mechanism. And this will generate emissions that actually may be used into the natural Earth system. So there is a complex relation. These models are used to generate the emission pathways, because once you write a narrative of what a possible world, then you have to translate that narrative in actual concentration of greenhouse gases. So in order to do that, you need elaborate models of the workings of the society, and so that you can estimate what kind of emission will correspond to certain political and societal choices. And you would get results like this. These are scenarios. Let's put it this way: every colored, all the colored dots are emission scenarios that were done at different times. So around 2000, for instance, you find IS 92, there were emission scenarios for 2000 done before, okay? So what is happening is that the actual emission, that's the black line, are sort of following the middle of the line scenario emissions. Well, two things, I think one we can take home from this picture. Well, the first one is that these people are pretty good. You know, these people have been actually writing, sort of imagining possible futures. And from these possible futures, they're trying to come up with certain emission amounts. And the kind of the portfolio, you know, the range of ideas that they've tried are actually bracked in reality. So this means that they're pretty good feeling through what may happen to the world. So they're not so crazy. The actual observations are within the envelope of this scenario. So that's, I would say, it's a very interesting observations. These models are good. Actually, it may point that our understanding of our society works is actually more advanced than we may think of. Yeah, usually we always say that it's impossible to predict societal development, but by looking at this picture, one has the feeling that indeed we can, at least in this sense. So that's first thing. The other thing that's interesting is that the actual emissions are actually tracking these scenarios that are somewhat in the middle. They're not tracking the really low one that you know, produce really low emissions. They're not tracking the really high ones. So it's interesting. Something is going on that is somewhat making the evolution of the emissions taking a path that stays away from the tail of the distribution. Now, in this present cycle, they've taken a slightly different view, that they have gone from giving a straight story. So, you know, the previous scenario, emission scenarios, where I'm thinking, you know, that the world will go like this, and this is the emissions. But people realize that because in the end, what matters is the amount of carbon dioxide and the other greenhouse gases in the atmosphere. You can reach the same amount for different reasons. And so they try to organize these possibilities in what they call shared socioeconomic pathways, SSPs. Now, these SSPs corresponds to basically different degree of implementation, of mitigation, and adaptation. So, for instance, the SSP1 group are basically a group of narratives where the world takes very good mitigation actions, takes good adaptation. So, you know, everything is it's working in a way, in the best possible way. Now, if you go up, the SSP5 scenarios are scenarios where people are actually being very weak on mitigation efforts. And therefore, there are, you know, in a way, a lot of emission. And then if you go on the right, on the low part, you go to SSP4. These are scenarios where mitigation is okay, but inequality is very strong. So the stronger countries are putting together good adaptation policies. The weaker ones are not. So this will be a world dominated by inequality. And then, of course, to go to SSP3, then that's the worst possible thing, right? So we get very little mitigation going on, strong divisions in adaptation. So this is a world divided. So let's put it this way, but there are rivalry probably developing among regional groups. And then the SSP2 that is somewhat in the middle between, all these, try to avoid all the extremes. Each one of these is a group of scenario, and they will generate emissions that are different. Some of these scenario will generate very low emissions, but simply because the economic growth hypothesized will be weak. So that's the other thing. The problem is that the emissions can go down because we are doing mitigation, or because the economy does not develop, and so simply the energy demand goes down. So so it's quite a different world if one way or the other, and so this has to be taken into account, even if the impact then on the emission may be similar. Just to give you a feeling, these are actually the global emissions of until basically a few months ago. And what we see here is the drop in global fossil emission. These are just from fossil fuel caused by the contracting economy last year. So you can see that it went down really quickly. That happens already in 2008, 2009, the other great economic recession. Then the emission of fossil fuel went down significantly. This time is much stronger. But you can also see that if you look at 2008, 2009, when the crisis is over, the slope of that curve stayed pretty much the same. So these sort of transient events are not going to change too much the secular trend, because when the crisis is over, then the growth more or less start again with the same slope, so with the same growth rate. That's of course because these are just in a way automatic adjustments to the economic dynamics. So this is not the results of policy at this point. But it's also useful to look at the energy use by source. So this is the split. So where we're what we use to generate energy. The interesting thing here, well, three things. Well, the first thing is that oil is still there, is still the primary energy source. The second thing is that natural gas is growing faster than oil. And the other thing is that coal has flattened. So coal is not growing, and we will see why it's grown so much. But the other thing to notice is that renewables are also have a very big growth rate, but there's still a small fraction of the overall energy demand. So we still have a long way to go before we can have a real mitigation in place. And if we look then at which one of these is contributing most to carbon dioxide emission, then we see that the carbon is, coal is the worst. Coal is the worst emitter. So using coal as an energy resource is about the worst thing you can do. But as you can see, it's been flattened because we saw the curve flattening. And then we have the other contribution from oil and gas, and gas is growing very much. Oh, sorry, I went back. It's interesting to look at the emission for a number of interesting countries. These are the emission by China. And you can see after year 2000, the enormous jump in the emission caused by coal, using coal in energy production. You can also see that in the last 10 years, the emissions have stopped growing. This is a result of a serious effort on the side of the Chinese government to curb coal usage. both for as part of their climate change policies, but also because such an extensive use of coal is creating severe pollution problem, and simply is not a good source. But this growth in China is actually reflects, where is it? The jump that you see in the global coal usage is mostly due to China. If we go and look at the US, what we see in the States is roughly a stable demand of oil and a growing usage of gas as a source. So in the later year, gas has overcome as a contribution to emission coal. But coal has been declining for 15 years. That's very interesting. Coal is basically dead as an energy resource in US for the past 15 years, and climate change has nothing to do with it. Coal is being phased out, not because of climate change policies, but because it's becoming quickly not competing with the natural gas. And that's why this is happening. And the net results is that emissions are basically being reduced because the contribution of the emission of coal is much higher than natural gas. So if the situation stays like this, the emission in US are probably not too bad. And this is Europe. Emission in Europe show the enormous jump in oil in the 60s and 70s. And basically a stabilization and then a slow decline. And also in Europe, coal has been declining quite a bit. Overall, Europe is decreasing emission, so they're doing a good job. But you can also see that the emission from natural gas have flattened and they stayed constant. So it's, Europe has made a pledge of cutting emission by 55% by 2030. That requires a concerted effort to actually do that. But definitely we're on the path to do that. And this is India. This is basically reflecting the economic growth of India. On the other hand, you have a very shy attempt of stabilizing coal, but India is also relying heavily on coal, but not the dimension of the Indian economy are smaller than the Chinese. So we don't see that very much, but nevertheless, the usage of coal is extensive. And we don't see any slowdown in the emission curve. Of course, they're also going to reflect part of the pandemic problem, so they will see a local contraction. But as I said, the moment the world gets out of the pandemic, I assume they will restart in absence of any serious policy with the same slope. And the rest of the world is showing similar trends. But I think the major thing is the growing importance that natural gas is actually having all over. And natural gas is a good stopgap measures to the road to mitigation and use of renewables, but eventually is producing greenhouse gases like the others. So we will have, to diminish the reliance on natural gas also. And this is the most interesting thing. These are the emission per capita. Global numbers are all nice and fine, but these are the emission per human being. And what's happening, this is a function of income, this is a function of technology level, lifestyle, and environmental conditions. Russia is a high fossil emission per capita, but that's also because they are, in a very cold place of the world. But US has a very high emission per capita. That's both because of the energy demand in US has reverted in the last 40 years. Now the peak, especially in electricity, is in the summer because of extensive use of air conditioning. So the energy consumption that reflects into the emission per capita in US is the highest in the world. And China is getting there. So they were growing very fast following the peak in the coal consumption that was seen before, and now it's flattening. And Europe is actually decreasing the emission per capita and maintaining a level of wealth. So this means that Europe is becoming more and more efficient in producing more wealth with less emission. So this is interesting. This is a sort of plastic representation of the kind of inequality that the climate change problem is exposing, and how much differences if the world is there, and they look at the emission per capita of India, that's really low, and so you can see how if the idea is that the full economic development will basically require the same amount of emission per capita, say, that Europe has, you can see what will happen to the world emission as the world gets, say, to the European level. Let's not say that we'll get to the American level, but let's say we'll get to European level. And that will be, so this graph show the absolute need for transformational change in the way our society produces wealth and our economy works, because we simply cannot sustain that this level of emission per capita at a global level. And so this is a very interesting story. And it's very easily, these are measuring tons per year per capita. Just to give you a feeling, a transatlantic flight is 1 ton per passenger. So if you go, well, nobody goes anywhere now, but if you go, say, to China or to United States and come back, boom, you have already spent your 2 tons of CO2, and you can easily go overboard. These are the projections for 2020. They're not very, we already discussed this, so we'll skip. So let's say a few words of how we approach this. Well, we're not approaching very well. I'm a physicist. I have discussed half of the time physical issue. The other half I've discussed probably rather inadequately economic issues. Here and there are, policy comments. The reason is that climate change is an inherently interdisciplinary problem. And it is clear that if you want to have an understanding of what's going on, if you want to produce useful results, if you want to have a scientific understanding of what is happening, we have to use an interdisciplinary approach. But how the academic and research community is organized, not very well. Well, first of all, okay, that's a slogan, okay? University have departments, society has problems. They don't match. Reality is that the traditional reductionist model is insufficient. Scientists are trained to look for simplicity. They are trained to look for elegant solution, as they say. That means solution with the simplest possible parameter. But there are problems that cannot be simplified. There are problems that have complexity inherently in it. And this does not make them less scientific than anything else. And these problems are messy, multidimensional, complicated. They don't suppose themselves to be treated simply or with simple concept. And so you have to consider, in a way, many factors at the same time. Uncertainties are high, so you have to include uncertainties into your evaluation. At the same time, there are emergence of new technologies that have the potential to empower many different fields. The tremendous advance in advanced data science, that's what we call machine learning, but that's really advanced data science analysis with new algorithms, new approaches, and especially powerful recursive approaches that have really given a new power to the capability of extracting useful information from the data. So this means that the pressure against traditional disciplinary barriers is increasing. Well, if you look at the science discipline, they're basically being designed in the 19th century. I mean, we use categories that are probably 100 years old. And the world has changed so much in the middle that that simply they don't seem to matter anymore. But nevertheless, the way in which the academic research system is organized is still, for instance, there is an excessive stress on individual work and not enough consideration or value given to the capacity of creating relational networks, because interdisciplinary work requires capacity to work together with different specialists, finding common languages and finding a solution can be traded across this disciplinary barrier. This means working in large groups. But the way the career and even the awards, the funding, and so on is organized is still not recognizing enough, and there isn't enough reward for people that engage in such complex and, in a way, time-consuming experiment of reaching over the disciplinary barrier. So I think we have a problem here. We have to find a new way in which we can get organized. We have to create institutions that respond to this need. And we have to find also the methods and the methodologies that will allow us to do this in a proper way. And to this path, a few years ago, there is a wonderful white paper by MIT that was called Convergence. And they're trying to push a new concept that goes beyond the traditional interdisciplinary kind of mantra, and is really thinking about the merging of distinct technologies and disciplines or devices so that to create a new whole. So it's not simply that you put together different fields or you collaborate with different research groups, but you integrate them in a way that you create a new body of common methodology and approaches. So it is a broad rethinking how scientific research is done. And what they had in mind really was the model of information technology and genetics. But from my experience in climate research, I can say that climate research is a prime candidate to convergence, as we need to put together this new body in which we look at the working of our planet, not only for the climate, just the physical climate, but we include the human society into that. And just the last thing, every country is organizing now national adaptation strategies. Basically must be scientifically based documents in which stakeholders are engaged, the decision makers, and then you try to put forward guidelines for building adaptive capacity in different economic sectors and space-time scales, look for proper organization, evaluate climate change impacts and risk, and finally identify and evaluate adaptation options, and that can be the base for informed policies. That is the plan that will actually operationalize the kind of science that we've been discussing so much, and will make those science the basis for effective policy. But adaptation has limits. This we can probably convince Dutch cows to do this if Holland goes underwater, but I'm not sure what happened with the cheese after this. And what are the consequences? Well, as we have seen at the end of this journey, there is increased risk. Increased risk means migration, people fleeing away from difficult conditions. We will have health risks or conflicts over scarce resources like water or agricultural land. That's one possibility. The other possibility is that this story will push us to increase solidarity, maybe a fair sharing of resources. Maybe innovation and technology will be the answer. We'll be able to develop innovation technology distributed widely, having an equilibrated green growth for the entire planet. Which one of these two choices? It will depend on us. No one can tell us which one we'll do. But, and of course, I don't know which road the world will take. But I can tell you that I think that policies will not be formulated due to climate change. So climate change will not be the reason for every policies that the governments put down. But I think it will be impossible to formulate any policy that does not take climate change into account. So climate change is going to be for us for a long time. And I think it's important that we contribute to this process with the only thing that we know, and that's our science preparation, our science method. And it's the only basis that will allow us to navigate such a complicated future. Thank you.
Thank you, Antonio. This is really something enlightening. I just take this opportunity to inform students that your presentation is on Virtuale, so it's available for download. And now at this stage, I think there are some questions in the chat. So,
okay. Oh, all right. Now I can see.
Yeah.
Oh, okay. Wait a minute. Okay. All right. One at a time. What do I think of the Green parties? Well, what can I do? I'm not sure what to think. Well, let's put it this way. As I said, I think climate change is an important issue, and it's important to raise the level of awareness. So I'm happy that people are taking it as a major political issue. I sort of think that is somewhat limited for a full-blown, general political initiative, but that's my personal thought. So the drop in the per capita emission in Russia after the fall of the Soviet Union was due to the collapse of the economy of Soviet Union in Russia. So that's an example of how emission can actually decrease for the wrong reasons. I mean, we don't want to diminish the emission because we're poor, right? We don't want to do that. So that's what happened. Oh, okay, that's interesting. That's about time scales. Let's see, if we would stop the emission, if we were able to stabilize emission right now, and so we will stop the growth of carbon dioxide in the atmosphere at the present time, the atmosphere will keep warming for about 20 years. That's because that's delay between when you put carbon dioxide in the atmosphere and the moment in which sort of completely express is warming potential. So I would say that when you start reducing the carbon dioxide, you will take, in theory, about 20, 30 years to start seeing the effect. In practice, it will take longer because in order to establish changes in the statistic of the atmospheres, it will probably take longer than that. So it will be a complicated issue, how to monitor in an effective way what we're doing. It is complicated right now. So that, I would say, is a very active field of research. Yeah.
Okay, any other questions? Yeah, I see a new message. No.
No.
No. Okay. If you have any other question, students, you're welcome. And of course, Professor Navarra will remain available to answer questions that you may raise in the chat in Teams. I will also inform you, Antonio, if I get any more questions.
No problem. Okay.
Okay, so I thank you again, Antonio. Thanks to Francesco. Thanks to Francesco and his colleague for the translation in Italian, and the lecture has been recorded. I will put it in the YouTube channel, just let's say within a few hours.
Okay, wonderful.
Okay. Thank you once again.
Ciao,
Grazie, Antonio. Ciao.
Bye-bye. Bye-bye.